Our next topic is probability. And so some basic terminology. We define the outcome as the result of an experiment. And so an experiment then is a set of conditions that we stage or impose. And so we measure the results. And all the possible results are referred to as the different outcomes we could have. The set of all possible outcomes is referred to as a sample space. The random variable is typically a numeric value associated with an outcome or one or more sample points in the sample space, and we'll go through some illustrations of that. And events can be the collection of one or more outcomes. Each point in the sample space has a probability associated with it, and so on things that we can count in a discrete fashion, we define the probability of an event as the number of ways the event can happen divided by the total number of possible outcomes. All right, so we toss a lot of coins and roll a lot of dice in this class, okay, to illustrate these concepts. Okay, so suppose then we toss two coins. The outcome is that we observe the head or we observe the tail. So our sample space then is the set of all possible outcomes. And so that what we have then in our sample space is we could have head on the first toss, head on the second. We could have head tail, tail head, or tail tail. Right? 4 possible outcomes. If we know what the order, each coin is different. Okay. Now then, let the random variable x be the number of heads observed. So that's how we define then a numeric value attached to events or outcomes in this sample space. So then what are the possible values for x? X can take the values 0, 1, or 2, since the number of heads we could observe would we have 2 heads here. There are 2 different ways we can get x equals 1, and only one way we can get x equals 0. Okay? And so that if we want to talk about the probability of 2 heads, our notation here, we can write probability observed 2h or just p 2h. So this capital P is just a shorthand for probability. Probability of the event, then you can write in the parenthesis. So in terms of the sample space, that probability of 2 heads is what's the probability of observing head in the sample space. Okay, so how many ways can that occur? Well, there's only one way head can occur, and there are 4 possible outcomes, right? Easy, I do the easy ones. We'll do harder ones, I promise. All right, so that would be the probability. In terms of our random variable x, that would be the probability that x is equal to 2. All right, so now if we wanted to know what's the probability that x equals 1. Okay, so in terms of sample outcomes, then that would be the probability of head tail or tail head. All right, so there's two different possibilities out of the 4 possible outcomes. And finally, the probability that x equals, we've got 2, 1, and so we've got x equals 0. So that would be the probability of observing tail on the first, tail on the second. That happens one way out of 4. Okay, so I know this is one simple, but just illustrates a couple of concepts for us. Probabilities are always between 0 and 1, and that if you add up the probabilities, if you add up across all the possible values of x, for us the values of x range from 0 to 2. The probability that capital X equals this script x, lowercase x down here, that this equals 1. We can define some other events. I'm right here at the edge of the paper, but I think I can get it on here. All right, that we can describe an event, say probability of at most one head. Okay, so what does that mean in terms of points in the sample space or outcomes in the sample space? So at most one head would be either head tail, tail head, or tail tail, right? So it'd be 3 out of 4. All right, so the actual values that you sum up across the values of x here x equals these individual values, those probabilities sum to 1. This is described here, this at most one head is an event. It's the probability of a sample point or some combination of them. Okay? In terms of the random variable, we could write this as the probability that x is what? If x is the number of heads, at most 1 would be less than or equal to 1, right? So we can either write our probability statements in terms of the random variable, we can write the probability statements in text, or we can write them as a list of the outcomes in the sample space. Okay? A discrete probability distribution is determined for a random variable x, and using this distribution we can find probability of events in terms of this random variable. So let's think about for the random variable x, we're going to let, and it's discrete here. So discrete meant what? No finer subdivision. So we're looking at x equals a particular value exactly, and not an x equal to some interval. So probability capital X equals lowercase x. My lowercase x is rather a script here. Suppose then I have this step function here, so say it's 5/9 for values of little x equals 1, it's 3/9 for values of x equal to 2, and it's 1/9 for values of x equals 3. All right, we can take and draw what we've been drawing as a relative frequency bar chart or a relative frequency histogram, as we'll come to learn, is that when we look at the probability of x on the vertical axis here and the values of x down here, it just looks like the bar chart where the heights then are equal to these probabilities, what we call the relative frequency. All right, so so I don't have to convert to decimals. I'll just 1, 3, 5, and 7. And ninths on each of those, right? So x equals 1 was 5/9. X equals 2 was 3/9. And x equals 3 was 1/9. All right, so the graph of a probability distribution, I guess we should say the discrete probability distribution, is the same as a relative frequency bar chart. In a second example, we could have that the probability of x equal to lowercase x. We could write it again as a step function. It's equal to 1/6 for values of x, equal to the integers 1 through 6, 1, 2, 3, 4, 5, 6, and 0 otherwise. Now in both of these cases, we could have put it equals 0 otherwise up here too. Notice that for each of the values of x that are assigned here, when you sum the probabilities, you get 1. Likewise down here, I'm adding up 1/6 6 times. The graph of this would be relatively uninteresting, right? Because it would just have 6 bars all of the same height. This is the probability of distribution associated with rolling a die, 6, right? say for the value observed when rolling a die. Say a single die. A single is die, two or more dice. And then I wrote dice anyway. Die. Okay, so graphing a probability distribution then isn't presenting any new information over what we talked about before. Now we just have this additional condition that the sum of these bar heights add to 1. All right, so these things that we observed when we talked about a probability distribution are referred to as probability axioms, so that whenever you have the probability of an event, the probability of the event is always between 0 and 1. So probability 0 means that it never happens. Probability of 1 is that it always happens. And as we saw in these events, then that was something in between. When you sum up the probability of events, given that the events are mutually exclusive, and so that means there's no overlap in these events, is what mutually exclusive means. So whenever you add up these events, and these events cover the entire parameters, the entire sample space, some of these probabilities must add to 1, which is what we saw there. So the way we wrote this just a short time ago is that the sum of the probabilities of x equal to all of its values, that sum must be equal to 1. Okay, so this is another way of saying it in the event notation. That's all there is on that. I didn't have any additional remarks to fill in. We can talk about complementary events. Given an event capital A contains one or more sample points in the sample space. The complement of event A contains all those sample points not in event A, and we denote the complement of A as an A with a superscript C. Some textbooks may use a different notation for the complement of a set. All right, and so it is the case that the probability of event A plus the probability of its complement, those probabilities must add to 1. And so, like I said, we roll a lot of die in here. So if we talk about that again here, so suppose we roll a die, and we want our sample space is what? We observe the value on the upturned face. The sample space then is the whole number of values, 1, 2, 3, 4, 5, 6. 6 possible outcomes, all right? Let x equal the number on the upturned face. We'll look at a way we can define the random variable to be something different than that. Let x equal the number on the upturned face. Or surface of the cube. Okay. Now, then in terms of an event, our event A, we could have let A be the event. Of a number no larger than 4. All right, so in terms of the outcomes in the sample space, what does A look like? It contains the values 1, 2, 3. Does it contain 4 or not? It does contain 4. No larger than 4. So it could be 4. Makes a difference. Okay, when we compute probabilities, what would the complement of A be equal to? Okay, the complement of A is everything in the sample space that's not in A. 5, 6. Now, in terms of random variable x, how do we write that? Event A. Well, we'll back up here. The probability of event A is there's 4 ways that can happen out of 6. So the random variable notation would be X. Sorry, you said it. Less than or equal to 4. Okay, which is of course 4/6 here also. And then the probability of A complement, we can see that there's 2 ways that that happens. All right, but using this rule, once we get into more elaborate events, all we would need to know is that we could take and subtract this probability from 1 to get the probability of the complementary event. All right, so we could write this then as the probability of X what? What's the opposite of less than or equal to 4? Strictly greater than 4. How else could we have written that in this case? We could have written it as greater than or equal to 5. Okay? When we have a discrete random variable, we can do this when we have that, so have this apparent jump like this. Whenever we look at continuous random variables, we're not going to be able to. Okay? But these are equivalent statements when I talk about this discrete random variable x and the values it can take, because we know there are no values of x in between 4 and 5 that occur with a non-zero probability, right? And of course, then the 1 minus the 4/6 we see over here is the 2/6. All right. So just to illustrate the terminology, we've looked at a couple of very simple experiments. It's the more difficult experiments that makes Las Vegas rich. Okay? So we want to look at another probability rule. We need to know the difference between a logical or and a logical and. Okay? And so in this experiment, again, consider that you roll a single die. We observe Y, the number on the top face. All right. So let's let for our example to illustrate this rule that our event A is equal to the values of Y such that Y is less than or equal to 4. Our event B is equal to the set of even numbers. All right, what is the probability of event A? And I just stuck with this die rolling experiment because we'd already introduced it. So the probability of event A, we saw that before, was 4/6 whenever I was using an X. What's the probability of event B? An even number out of these, so there's 3 out of 6. Agreed? Now in this very small data set, what's the probability of A and B? Okay, so to the side here, if I make an illustration, our sample space will have 6 points. One of our circles in our Venn diagram will represent event A. The other will represent event B. Event A has values that are 1, 2, 3, 4, and B are the even numbers. And so I didn't leave enough space here. 2 and 4 are in both, right? 1, 2, 3, 4 are in A. 2, 4, 6 are in B. And where's 5? It's out in the sample space. It's not in either one of the events, right? So the idea here, if I know the event A is 4/6 and the event B is 3/6, I can't just add those probabilities together. All right, because in this particular illustration, I have a problem. What is that? Probabilities exceed 1. Okay, when you have a probability greater than 1, it's not a sure thing. Okay, well, the only thing that's certain or sure is that you've made a mistake. Okay, so the reason this is, in this case, is adding up to greater than 1 is we've got some overlap here. Now, they won't always go greater than 1, so I've picked it so that it did clearly. All right, but we want to illustrate with this very simple example this probability rule. Okay, so or means it could be either in A or B or both. Okay, and means it can only be here in this middle part. A and B must have it in common. Okay, so logical or says it could be in this circle or both. Okay, so if I count those, then the probability of A or B, we can see that it is the set of numbers 1, 2, 3, 4, 6. And so we know there are 5 ways that can occur out of the 6 possible outcomes. And so I can't count the 2 and 4 twice. Okay, because if I take the probability of A, I'm picking up the occurrence of 2 and 4. And if I count event B, I'm picking up 2 and 4 a second time. So I don't want to count things twice. So that's why we're subtracting off things that they have in common here. Okay, and so that whenever the probability of A and B, then, that we see there are 2 ways out of 6 that happens. All right, so that if we wanted to look at the probability of A or B, all right, we have the probability of event A plus the probability of event B, but we have to subtract those that we've counted twice. And then we get 5, 6, which is what we see in the Venn diagram, and logic kind of helps us figure that out. And once we get into the more complicated stuff, all right, we need to be able to use this rule, but to just, like I say, to demonstrate how it works on a very simple problem. All right, we can also define independent events, so that events A and B are independent events if the occurrence of A does not influence the occurrence of B and vice versa. All right, so when we write probability B given A, the notation for that is a vertical bar, red given that. So event B given that A has occurred. So if A doesn't influence the occurrence of B, then B given A would be exactly the same as the probability of event B. Okay. Likewise, we could have that if it were the probability of A given B would be equal to the probability of A if they are indeed independent. All right. If these equalities do not hold, all right, then the events are dependent. Okay. Whenever you look at a logical AND, the probability of both events A and B occurring is equal to the product of the individual events if and only if A and B are independent. Okay, what does that mean? All right, this says if and only if means then that if this probability statement is true, that implies A and B are independent. If A and B are independent, then I know this probability statement has to be true. So if and only if means that reads both ways. Okay? So if this probability statement is true, the events are independent. Okay? The reverse of that, if they're independent, I know this probability statement has to be true. If they are dependent, then this equality may not always hold. There may be some coincidences where it does. All right, but if they are dependent, this doesn't have to hold. Okay, so some illustrations of that. So consider the following hypothetical classroom demographics for Stat 5013. All right, I have master's students and PhD students, males and females. Doesn't look like it's this summer since we're kind of lightly enrolled, aren't we? All right, but the breakdown of the students in the class, say, looks like this. All right, so altogether in the class, I have 30 males in the class. There are 20 females. Master's students, there were 32. And PhD students, there are 18. If I add those together, I get 50. If I add it together this way, I get 50, right? So I have a class of 50. Everyone's looking around going, where's everybody? All right. So the probability of, if I selected a student at random from the course, what's the probability that that student is a male student? How many ways can I can select male is 30 out of 50 possible, right? Easy enough. Are the events of master student and female independent events? So the idea here is that if the probability, how do I want to say that? Is later we'll talk about how to test this association and test this independence, but are the females in this course more likely to be master students or PhD students, or likewise, or males in this class tend to be one or the other, or there doesn't seem to be a trend? Okay, so that's actually something we'll be able to assess or evaluate later in the course. All right, but it helps us illustrate this idea of independence here. So our master student and female independent events. What's the probability of observing a master student? $32 out of 50. I think I heard somebody say. What's the probability of observing a female? $20 out of 50. Either by looking at the above table or subtracting this from 1, right? Female, male, complementary events. What's the probability of a master student and that the student is female? Okay, that would be just these 12 in this cell of the table, right? Out of how many different ways could I select out of the class? There are 50 students still. Okay, are they independent events? Okay, so we want to look at this rule on the previous page. The probability of A and B, is it equal to the probability of the product of events A and event B? Okay, get all that to fit on one page. So what do we have here? All right, so how does this 12/50ths compare to the product of 32/50ths? Probability of event A, probability of event B, it's 20/50ths. How do those compare? Are they equal to each other or not? And with a quick check, you can find that they're not. And so, are they independent events? No, there's some association there. Now, how strong it is, we haven't made that assessment yet. Okay? Yes?
When you switch the paper, which formula did you use?
This one right here. Should have put it at the bottom here. So the A and B is this 12/50ths. Event A times event B are these two. All right, so far I've chosen things that have been pretty easy to count, right? 4 outcomes, 6 outcomes, 50. Things are easy to count. Not everything's that easy to count. There's a reason I start with the easy ones. All right, so now then we need to talk about some different ways of how can we count the number of possible outcomes, because not everything's quite that simple. Okay, so we first define a multiplication rule. If there are k sets, each containing ni elements, then there are the product of n1, n2, to up through nk possible outcomes of these elements. All right, so the value of I, this says that if there are k sets, All right, so n sub I ranges from 1 up to k. So each of the k sets has ni possible elements. We multiply those together. So our Oklahoma license tags that we're driving around with, okay, they have 3 letters and 3 numbers on them. How many tags are possible? Okay, so we want to think about how many sets there are. So the idea is with 3 letters and 3 numbers. So which are we now? We switched a few years back so that we are kind of our three numbers and 3 letters. Okay, and I have k sets. My k is equal to 6. How do I fill each one of these slots? Right? Okay, so how many different numbers can I put here? Well, I can go 0 through 9, right? So there, in each one of these places, I have 10, multiply times 10, okay? How many different letters can we use? Well, if every letter combination is available, that's probably a risky assumption, all right? But let's suppose it is for now, okay? So that means the 26 letters in the alphabet, so I have 26 different ways to fill the first blank, 26 ways to fill the second, and 26 ways to fill the third. How many car tags is that? You can probably be surprised. Bigger than you thought? No? 17,576,000. And if there are still some of the, I want to say, older tags available, in that case the letters were first, the numbers were second, right? So we'd have plus that another 17,576,000 when we have the letters first, numbers last, right? So what if, this is my W, what if no letter can be used more than once? Then how many car tags are there? Doesn't affect the numbers, so I know I'm still going to have 10 times 10 times 10 or 1,000 here. What about the letters? When I go to select the first letter, I have 26 letters available. In the second space, only 25, and in the third space, 24, because we can't use them more than once. Okay? That value is equal to what? 15,600,000. Still a lot. I bet there's more letter combinations they don't allow. Don't you suppose? Okay, we don't need quite as much space as I've budgeted on these next two, on this next page. How many tags are the form AB something? Pardon me, I went here with letters first. Okay, that's all right. So I did numbers first, letters here. So if I switch this around to letters, numbers, that's our old style. I didn't realize I needed to flip that. Okay, if letters are first and numbers are second, how many tags have this form AB blank and then 3 numbers? 26,000, because why? 26 ways to fill this blank, and then assuming that all numbers are available, so that's where you end up with the 26,000. So if you select a tag at random, what's the probability of getting an AB tag? Assuming just among the letters, numbers, that way. What's the probability of getting an AB tag? So assume 3 letters, then 3 numbers. The previous one I had 3 numbers first. How many ways can you select an AB tag? 26,000. How many ways can you select a tag? 17,576,000. That's equal to what, decimal-wise? Rounding to 4 decimal places. Let's see. 001479. Keep going. Is that very likely? Better than your probability of winning the lottery, but you play anyway. All right, sorry for that bit of confusion about the letters first there. So I'll try to... Okay, so that's multiplication rule. Now, the multiplication rule kind of also took that idea of independence and dependence. It's like if every letter is possible, as soon as we put that condition on there, no letter can be used more than once. Now the selection of the second and third letters weren't independent of the first letter, were they? Okay, so so just a kind of a side note, we'll come back to that. We can also use a counting technique, which is a specific case of the multiplication rule, where you have an ordered arrangement of R distinct objects selected from N objects. This is called a permutation. There are different notations for permutation. Again, this isn't there's no one uniform notation. So the number of permutations of n objects taken r at a time is given by this expression, this n factorial over the quantity n minus r factorial. So where n with the exclamation point doesn't mean say it real loud. Okay, it's not like it's not n shriek, similar to our f shriek that can show up on transcripts, which we hope never does. All right, but n factorial just means then that this n is an integer value and a positive integer value. You take its value and then multiply it times every integer smaller than it until you get all the way down to 1. Okay, by definition, 1 factorial is 1, and since here the last thing in the product is 1, but 0 factorial is defined to be 1. Okay, and so so the way this is read, then I said it is n factorial. You probably have a factorial function on your calculator. Some calculators will have a permutation function. All right? So suppose we have 3 students from a group of 12 are to be selected to serve as officers for the group. The first person selected will be the president of the group, the second will be vice president, and the third will be the secretary-treasurer. How many different slates of officers are possible? Okay, order's important, right? That's what makes this a permutation. All right, so what we have here is that we have a possible 12 students, and we're selecting 3 of them. Okay, and so then by this formula, how many different slates of officers are possible? Then we'd have 12 factorial divided by 12 minus 3 would be 9 factorial. If you have a factorial function, you can multiply those out. It's easy. So the factorial, this means we're taking 12 times 11 times 10 times 9, so forth, all down to 1. But once I get here, beyond that, we can just stop at 9 factorial. I want to cancel it with this 9 factorial. So 12 times 11 times 10 is, well, 12 times 11 is 132, times 10 is 1,320. So for that one little group of 12, we have over 1,000 officer combinations. Because order was important, right?
The 9 factorial at the end, where you plug it over 10, 9,
Mm-hmm.
did you just pull that from the denominator of the previous one? Is that where that comes from? Where did you?
Rather than write out 12 factorial, rather than write this all the way out down to 1, I know from 9 down to 1 is 9 factorial.
Okay, so we could have gone ahead and.
Yeah, you could have.
It would go down to 1.
Yeah, you could take this all the way down to 1, but then you'd be canceling 9 with 9, 8 with 8. So it was just easier to cancel the 9 factorial. Okay, so this is, if we make the selection and order is important. Okay, nobody wanted to run, so we had a random drawing for officers, right? Okay, so what if you're trying to draw a committee of equals? So order's not important anymore. Okay, how many different committees could be chosen? All right, so let's just consider 3 students in this group. So let's consider students A, B, C in this 12. Okay, so in terms of slates of officers that I would have, if A is president, B is vice president, secretary, treasurer, ACB, BAC, BCA, CAB, CBA. All right, so for these 3 officers, there are 6 different slates we could have as officers. Now, as a committee, all 6 of these are the same, right? Okay, so as a committee, these selections are equivalent. Be a better way to say that. If order is important, they are different. But if order is not important, then committee ABC is the same as committee CBA, right? So I don't want to use a permutation because the permutation is going to give me this duplicate information, right? Doesn't account for duplicates. I need to divide out all the possible duplicates, right? Okay, so that's referred to as a combination. When order is not important, we compute a combination rather than a permutation. And so the combination here, we have a parenthesis, n over r, and this is read as n choose r. All right, and so what we see here is n factorial divided by n minus r factorial. That's the permutation, right? Divided by r factorial, that's dividing out the duplicates. All right, so for us, then what if our committee of 3 students can be chosen from the 12? How many committees are there? So it would be 12 choose 3. And we write then 12 factorial over 9 factorial. That's the permutation. Divide out the duplicates, which is 3 factorial. 3 factorial is 6, because for every 3, I have 6 duplicates, right? That's what 3 factorial is. Okay, so we can do this the same as we did before. 12 times 11 times 10 times 9 factorial. I'll have the 9 factorial cancel, and then I'll have the 3 factorial is 6. All right, so I end up with the 1,320 permutations. Divide out the duplicates of 6, and so that I would have 220 different committees that are possible. Okay, so far? suppose you are one of the 12 students. What is the probability that you will be chosen as president? How many ways can you be president? How many blanks do we have to fill? Think of the multiplication rule. Okay, president, vice president, and the secretary treasurer. You, a vice president, and the secretary treasurer. How many ways can we select you? One. All right. How many ways can we select a vice president? If you're one of the 12, then it's got to be one of the other 11. And then how many ways are left to be secretary treasurer? Would be 10. All right, so there's 110 different ways you can be president. What's the probability that you are president? How many different slates of officers were there? Okay, because that's that counting technique. Number of ways you can be president divided by total number of outcomes, right? Go back to that very first definition of probability. So number of ways the event can happen is 110. Number of possible outcomes is 1,320 or 1/12. We really didn't need to go through these second two. It's just if you're the first one, right? What's the probability you would be selected for a committee? Okay, illustrating these rules. So how many different ways? So number of different committees. You could be on would be equal to, there's you. And then how do you feel out of the remaining 11, choose 2? Right? So those 2 blanks that are left is a combination. All right, so 11 choose 2 would be 11 times 10 times 9 over 9 factorial divided by 2 factorial. 110 divided by 2 is 55. So the probability that you are on a committee would be equal to 55 out of how many committees are possible? 220. 1/4. All right, what I wanted to demonstrate there are some other ways you can reason through that. I wanted to demonstrate for you, though, the multiplication rules. So here, just the number of ways this can occur. The second 2 blanks for the committee you can fill with a combination. So you can take a combination times a combination, because this is really 1 choose 1, right? Okay, you can just go back to the bare definition of multiplication rule, or you can talk about permutations. That's how we did the denominator as a permutation. The denominator here is a combination. Okay, so there's different ways you can approach these counting techniques, so we can, that multiplication rule works. All right, if you're not a card player, I'm sorry, we'll do one here. In the card game of poker, each player is dealt 5 cards from a deck of 52. 13 cards of each of the 4 suits: spade, club, heart, and diamond. What is the probability of being dealt a pair of queens? You have jack, king, queen, ace. If you're not. So Q equals queens. And clearly I'm not doing Texas Hold'em. So I'm not wearing my sunglasses. How many ways could you be dealt 2 queens? There are 4 in the deck. You have 5 cards, number of ways to get 2 queens. So you have, and 2 blanks we'll think about. Queen, no queen. So how many different ways could you get 2 queens of the 4? So that'd be there are 4 altogether, and you're getting 2 of them. Order's not important, is it? No. Okay, your remaining 3 cards come from the 48 not queens, right? So I have 48 remaining cards, and from which I draw 3. Queen, how do you number of ways you fill the queen blank times the number of ways you fill the no queen blank, multiplication rule. So the number of ways you could be dealt 2 queens is equal to I have 103,776. Do you agree? Now, is this number specific to the queens? No, it's the number of ways you could be dealt any one pair, right? Okay. How many ways? So if you have 2 queens, so how many? What's the probability of 2 queens? Well, how many different ways could you receive 5 cards of the 52? Right? That's the number of possible outcomes, isn't it? Okay. So the number of ways. 5 cards can be dealt to you. That's going to be equal to 52, choose 5, right? I have 2,598,960. Do you agree? So what's the probability of 2 queens? The 103,776 in the numerator, divided by the total number of possible ways you could receive 5 cards. And when I divided that, I got 0.0399. We could go on some more, to 4 decimal places. So not just specific to queens, but so for any single pair, your probability of drawing a pair is 0.0399.